Thanks a lot, Amita. Thank you so much for inviting me. It's been a long time since I've come here. Also, last time Amita invited me, so it's a real pleasure to also see him. He's 1 year, right? He's senior to me, so it was really nice. In Syracuse, we were just reminiscing our old times. Um, so I've been told it's a mixed audience, and what I'm going to do is, so my main goal is not to complete the talk and give you the technical details. This happen. The working metric and memories. So the main goal is basically to tell you what the issues are, and then of course there is a model and there are some technicalities and so on, and I will go through those, but terminate at any point. There's no problem. Please tell me either to go faster if you know what I'm talking about, or to slow down if I'm going too fast. So let me start. That's the title of my talk: spherical collapse and black hole evaporation, and we'll see what the goal of this whole exercise is. Before that, let me just give you some kind of review and introductory remarks because I'm a relativist by training. Sort of the things we use in our bread and butter may not be familiar with other backgrounds. So let me just tell you a little bit about those things. And one of the first things one encounters in this business is these things called Penrose diagrams. So what are Penrose diagrams? They are handy ways in which to represent space-time. And in this talk, I will only be talking about spherical symmetry. And what a Penrose diagram does is that it, via coordinate transformations, it takes infinity and brings it to a finite distance. So, for example, it's just a generalization of what you would do when you compactify the straight line to the circle. So, you just take the transformation 1 over x, and x goes to infinity, is identified with x equal to 0. So, you're bringing infinity back to a finite point. So, here also, there is a more sophisticated way of doing this. The important thing is that when you're doing this, when you're bringing infinity to a finite distance, whatever you're doing, you're not changing what is called the conformal structure, the causal structure of space-time. That's a fancy way of simply saying that over here, light rays will always go at 45 degrees. So you're making that, the transformation makes that possible. That's very handy for what you want to do. So the concept of space-like, time-like, and null events are just very easily read off from Penrose diagram. So it's possible to do this, and that's what we do. Now, if you're in spherical symmetry, it becomes particularly nice because in these Penrose diagrams, every point here you can think of as a two-sphere. So if this was not 4 dimensions but 3 dimensions, then every point would be a circle, and you could just think of this as circle, right? So you just rotate it around. It's very so circularly symmetric, spherically symmetric. So it's in 4 dimensions. So every point here is a circle. And for example, okay, and now what are the infinities? So you have this guy over here, and this is the place where if you take any light ray and you ask where it originates from, it originates in the infinite past. Like you can sort of extend it all the way back, and that place is infinitely far away. You bring it to a finite distance, and that is called past null infinity. And it itself happens to be a null surface, quote unquote. It's not really part of your space-time, but you're bringing it into, give it a home to all light rays, which are then the infinite past. You look at all objects which have mass. So all time-like trajectories in the infinite past, they originate over here at a point which is called time-like past, time-like infinity. And then you have all the light rays. Where do they end? So you keep on following them for infinite time, and they end over here at a place called the future null infinity. And Penrose would denote these by script I. So that, and so in relativity we just call these scry, right? So this is called scry minus, this is called scry plus. In terms of these definitions, what is a black hole technically? So technically a black hole is the following. So here I've drawn, again, this is clearly a time-like trajectory, right? So that's the beauty of these Penrose diagrams. That 45 degrees, and you know what is time like and what is space like. I forgot to tell you that a place where all space-like geodesics originate or terminate is called space-like. That's over here. That's where you read of things like the mass, ADN mass, and so on. Now, what is a black hole? Black hole is the following. Supposing you go and you climb onto Scribe Plus, and you look down upon the space-time from Scribe Plus, and you don't see all of the space-time. It's part of the space-time which you don't see, which means that light rays from that part of the space-time do not terminate with infinite uh, time at your Scribe Plus, because that is a place where all light rays terminate after exhausting infinite time. Okay. So if you go back and you look at the space-time, then clearly this part over here is not visible. And so you say that this space-time has a black hole. Right? And this wiggly line over here represents a singularity. So that's where the curvature goes up. So in this particular geometry, it's depicting something which has a future singularity. And this last light ray, where you just about, it's the boundary of what you can see and what you can't see from Scribe Plus, that is the horizon. And since we have said that this is, every point is an S2 a sphere, but the horizon is a three-dimensional surface, just topology S2 cross R. So is that clear? Now, there are some subtleties over here, and one subtlety is the following. So one can just take flat space-time, do the same exercise, bring infinity to finite distance, etc. And flat space-time is in particular spherical symmetry. So we can still draw Penrose diagram here. And I can simply chop off part of flat space-time. Just chop it off, right? Now when I go to Scribe Plus and I look down, because I've chopped off this part, there should actually be a triangle over here. Because I've chopped off that part, I look in over here, and again I don't see this part. So you think, okay, technically the definition is such that there is a black hole, but they can't. This is just flat space-time. So what happens over here? What is the difference between this and this? The difference between these two is that if you have an observer here who shoots a light ray, any place over here on Scribe Plus, by the time it comes to this point, that light ray exhausts infinite affine parameter. So it hangs around for infinite time. Whereas if you look at a light ray over here and you shoot it, it just abruptly ends because you abruptly cut off the space-time. So you find that in a finite time, it just has to stop. Okay. So this technically is called an object which is not complete, not geodesically complete, whereas this is geodesically complete. So part of the definition of a black hole, or part of the definition of Scribe Plus, is that Scribe Plus has to be complete. So you take a complete Scribe Plus, you look back, you don't see something, there's a black hole. All right. Now it's very, and this sort of a definition. This sort of a definition of a black hole is where all the black hole thermodynamics, black hole entropy, which Wittgenstein found, and so on. The fact that black hole entropy always increases, the area of the black hole increases, even merger, etc. This all has to do with the event horizon. And one really awful thing about the event horizon is that clearly you need the whole space-time to be able to say where the event horizon is and whether there is a black hole. So this is called the teleological aspect of the definition of a black hole. It's a mathematical definition, right? Physically, it's of no use because you can't wait infinite time and then see whether there's a black hole or not. But this is what all the theorems and so on use this. Okay. So much for Penrose diagrams and black hole. Let me give you an example of a black hole solution. And this is an example due to Professor Vaidya, who have probably passed away a few years ago. But at least in the GR conferences, there were fixtures. Professor Amal Roy Chaudhary and Professor Vaidya. They would both come, they would sit in the front row. Professor Vaidya would have a Gandhi topi and a glove there, very quiet. And of course, we were all, I was too junior, I was in awe of both of them. I shouldn't have been, but I should have gone up and talked to them. I always regret that. And Professor Vaidya's solution was ages and ages ago. And, I mean, thing, Amitabh, all of us become old, we tend to sermonize, right? So I will sermonize a little bit. I just wanted to know that whether it is Professor Arch or probably Professor Ghost over here, or they had almost nothing. They just came and they did physics under all sorts of crazy circumstances and produced like work which I am not capable of producing. Raman also, you would just hang around here and one day went to cultivation with this thing. So whenever we complain that we don't have this facility and that facility and this is not going well and that is not going well, then it is also good to look at those people who never had anything and did all this fantastic work. Okay, sermon over. So what is this Vaidya solution? I am drawing a Penrose diagram. So in this Penrose diagram, now we are all good. It's a spherically symmetric solution. Okay. So again, you have past null infinity, you have future null infinity, you have a singularity, and you look down, you don't see the whole space-time, so there's a black hole. But this is an explicit solution in which you can give a metric, Vaidya give a metric, and it describes spherically symmetric infalling null test. So the metric, when you write down a spherically symmetric metric, you have an angular part. Right? So you have angular killing fields, and the orbits of those angular killing fields are two spheres. So nothing depends on the angle, and the radius or the area of these two spheres is basically 4 pi times capital R square. So this angular component of the metric carries information. If you multiply it by 4 pi, then you get the area of a spherical object of symmetry. Right. So these are the symmetry spheres which have radius 4 pi r square, which have area 4 pi r square. So R is called an aerial coordinate. That's the area. And then you have, since these are two dimensions, you have over here 2 dimensions there, signature minus and plus. So there's a 2-dimensional metric. And in the case of the Vaidya solution, it turns out that you can actually use this aerial radius as one of the coordinates. And the other coordinate, I'm just going to call V, and the lines of constant V turn out to be null lines. They are 45 degrees. So these green lines are matter. This is the null dust which goes along V equal to constant lines. It collapses and there is a singularity over here. So the green lines over here are null dust trajectories along V equal to constant lines. I have not given you the form of the metric because it's not particularly enlightening. The main thing is that the stress energy tensor is prescribed as a function f of v, and this is intimately related to the mass of the space-time divided by this 4 pi r square. So this is like a spherical wavefront of area of 4 pi r square and some null dust which is propagating, and as it propagates inside, it tends to, like all spherical wavefronts, tends to focus, and when it comes, this is the axis. Right? So this is the axis of symmetry. If it was just a circle, as I said, you would just go around like this. Right? So this part is the r equal to 0 axis of symmetry. Right? So nothing. R equal to 0 looks as though it's a singularity, but that's just a coordinate. It's a usual coordinate singularity. So if you had flat space-time, or even flat space in polar coordinates, right? You are dr square plus r square times something. R equal to 0 looks as though the metric is not well defined, but you know actually in Cartesian coordinates that everything is well defined. So similarly over here, this is the axis. There's nothing singular about it, and you have a stress energy, and the moment it hits the axis at r equal to 0, the stress energy blows up, and you have a singularity. A very interesting feature of black holes is that light gets trapped. So what does that mean? In spherical symmetry, you can actually visualize it much better. So imagine that you have a sphere. This one you have a sphere. You can sit on the sphere, and you can. There are two kinds of light rays which you can take a torch, have observers on every point of the sphere, and you can either shine light inside, inward, or you can shine light outward. And clearly, the inward, because of the initial conditions, inward, right, and whatever is the geometry, the ingoing light rays will all converge. Right? The outgoing light rays will diverge. That is the standard normal behavior in flat space. But once the space-time gets curved, all sorts of crazy things can happen. In particular, what you could imagine happening is that you take the sphere, just right, in an adequately curved geometry, and the ingoing light rays, they converge, but the outgoing light rays just are between the borderline of diverging and converging. So they are like collimated beams. So basically what happens is that if you shine these light rays, outgoing ones, right, then just nearby spheres are of the same area as the sphere. So it's a very non-flat space-time equation. Flat space-time, you would have spherical light fronts like that. Here they're collimated somehow. Okay? That is just the geometry. It's a curved geometry. So what happens over here is that this blue line, remember that every point here is a sphere. So every point here is a sphere. And the geometry is such that if you go outside over here, then the behavior of light is like normal, like what we say. If you go inside here, right, then both the ingoing light rays as well as the outgoing light rays are converging. And where do they converge to? They converge to the singularity, right? Not go. They only have to. They cannot come out. And this boundary is where the ingoing light rays remain convergent, but the outgoing light rays have basically what is called zero expansion. They neither converge nor diverge. And this is called, therefore, what is inside is called a trapped region, because light is just trapped inside. And what is outside, this boundary is called a marginally trapped surface. So this is the beautiful behavior of light in curved space-time. And in fact, this marginally trapped surface, what typically happens is that the Einstein equations tell you what happens to a marginally trapped surface when you throw in matter. And typically what happens is that the area of this marginally trapped surface, the area of the two spheres increase. Don't confuse that with the fact of the light fronts, whether they are diverging or converging. The outgoing light fronts are always between converging and diverging. They have zero expansion. But if I go over here, for example, I have a sphere which is just at r equal to 0, right? Just a point. As I throw matter in, this sphere starts increasing in radius. These spheres which all populate this marginally trapped surface, they increase in radius. And over here, once the matter is stopped falling in, these spheres exactly take the area r square equal to whatever, 4m square, r equal to 2m. So this marginally trapped surface then matches with the event horizon. And you know, in Schwarzschild, you have spherical symmetry of Birkhoff's theorem. So wherever there is no matter, you essentially have Schwarzschild if you have mass. Over here, because the matter is not fallen in yet, here again by Birkhoff's theorem, you just have flat space time. So you have flat space time here, you have some curved space time here, and this part is like Schwarzschild. And this is the event horizon, which is at r equal to 2. And the event horizon, you know, has a constant area, right? Because r is equal to 2m by definition. So r doesn't change, and these are sort of the last outgoing ray which just about meets it. So everything comes together. Yeah.
I don't know if you'll address this later on, but do you know about trajectories inside the event horizon?
Yeah. So inside the event
horizon, matter and light ray, do you know trajectories inside the?
Yeah. So there you can just compute the geodesics, and you will know, and they are basically trapped. So you will find, and that is natural because everything has to finally fall into the singularity.
Yes. Okay.
So what happens is that if you start, for example, at a little bit r less than 2m, right, and both sets of light rays will start converging. Even the ones which are going out will hit the singularity here at r equal to 0. So it is going from r equal to 2m here to r equal to 0 here. And this is going from r equal to 2m, but this is converging because you already knew that those were converging. Any question, just stop me. As I said, my purpose is not to rush through the seminar and give you some technical results. This is fun for me, so whatever's, and it's really beautiful stuff. Anyway, all old stuff, standard, but it's fun.
Is there a special reason for using dust?
So that one would have to ask why how we came up with dust, but it's very hard to find exact solutions of the Einstein equations with matter. and that too now describing a black hole with collapse. So this is what he found. It becomes exactly solvable for this purpose. So that is why even the Schwarzschild solution was like a total revolution. I can't resist it. I give a 2-minute story about Schwarzschild because I read up and I think it's maybe well known, but the details may not be well known. Schwarzschild he was an astronomer. He's already a very well known astronomer in Germany. He was up, sort of on the up. He was in his late 30s, just about to hit 40. He had just been um, he had worked on telescopes, actual telescopes. He had also heard in the late 1800s, he had heard this, I don't know if you guys are aware, there's a famous address by Riemann, where he hinted at the possibility that physics would have something to do with the geometry of space-time before Einstein. So there was a strand of German physicists who were thinking about these ideas, and Schwarzschild had heard this lecture, and he also was cognizant of this. So he had done lots of, he had even worked in, he was an incredible guy. So he was, I think, just about transferred to Potsdam, and it was the highest honor to take care of the astronomical facilities in Potsdam. When the First World War broke out, he was apparently a very optimistic, happy guy. That was his personality. When the First World War broke out, he chucked everything and he volunteered actually. Out of a sense of patriotic duty, he volunteered to serve. So first he was, he's put in France and Belgium, I think, where he was computing these missile trajectories. And finally he was sent to the Eastern Front. Now that was already, almost 1914, late 1914, 1915. And at the front, so there were all these missiles, real war over there. And at that time, Einstein just about, after all these struggles of 15 years, finally completed his general health. He had many blind alleys, different offices, blah, blah, blah. And Schwarzschild received on the battlefront this set of papers. And these differential equations are terrible. They are nonlinear coupled partial differential equations. Nobody knew any solutions, right? And Schwarzschild, within 3 months, I think, he found this Schwarzschild solution. Okay, and probably because he was already familiar and had been thinking about Riemann's address. Not only did he find this Schwarzschild solution, at that time, simultaneously with that, he contracted a terrible autoimmune disease of the skin. The skin started attacking itself. Body started attacking itself. Horrible. And there was no known cure. So he was dying. He was dying, and he has written a letter to Einstein saying, with this solution, and I don't have the exact quote, but he has written that, and so you can see that, even while whatever cannonballs are flying around me, I still have some little bit of time to think about physics. Right? So, and then he published the solution, and shortly after was discharged, and he died. So again, this joins, the same lesson. All these people, they struggle, and then I wonder, like, why the hell do we complain that this thing is not working and my something? These guys just did things which are unbelievable. Sorry for that long digression, but I thought you might find it nice. Okay, so let's go ahead and let's talk a little bit about sort of I'm coming to where I want to come with this problem. Which is the Hawking information loss quantity. Now, the very definition of a black hole is that nothing can come out of it, right? Because you go all the way to null infinity, not even light reaches you over there from that part of space-time. Now, there is a lot of other beautiful stories which I don't have time to tell, which has to do with black hole entropy, which has to do with Jacob Bekenstein, and so on and so forth. But suffice it to say that what Hawking did, building on the work of Leonard Parker and other people, was to consider on the background, so on this fixed background of a curved space-time with a black hole, to consider the behavior of quantum fields. Because it's well known, and probably you also, that time-dependent fields have the possibility of creating particles. It's like an external field which is time dependent, and it can start creating particles. In this case, the creation of these particles is called Hawking radiation. So there is a detailed calculation which goes under this quantum field theory on a fixed space-time, and it turns out that the conclusion of this calculation is that at very late times. So what does one mean by very late times? By very late times, one means this part of scrap. Very late. This is early part, the late. This is the infinite past. This is the future, but the early future. This is the late future. So at very late times, he was able to get a kind of very simple and nice form for the kind of radiation which the black hole emitted, and it turns out that it emits completely thermally. So it emits radiation, whatever is the field you put over here. Right? So you put some field at some null. Simplest to put a zero mass field here, and you look at what happens to it over here, and you find that it's populated with particles. Right? So you say the black hole is radiated particles, and it radiates at a temperature called the Hawking temperature, which is inversely proportional to the mass. It's a very, very low temperature for an astrophysical sized black hole because you have these factors of the Planck mass all over the place. But it is goes as 1 over mass, and therefore what happens is that as the black hole radiates, you expect through energy conservation that it loses mass, and when it loses mass, its temperature increases. Its temperature increases, then of course it has more radiation. So basically, it has negative specific heat. However, this process is extremely slow, and you can estimate it as follows. So there are two time scales which are important in this estimation. One is the evaporation time scale. So you can just take the mass and divide it by the rate of mass loss. What is the rate of mass loss? It's a usual Stefan Boltzmann radiation thermal law, where the area of the object, you take like its Schwarzschild radius squared, and you have the Hawking temperature to the fourth, and you plug all this in. Now, there is another time scale, which is that you imagine that the black hole radiates, and then it kind of settles down. How quickly will it settle down? That time scale is roughly the time scale at which one part of the black hole communicates with the other. So, if you take the size of the black hole to be the Schwarzschild radius, and you say that, well, general relativity, gravitons, etc., they are massless objects, so you can put the speed of communication and speed of light at another time scale, right, which is this Schwarzschild radius divided by the time. Now, if you take the two time scales, the settling down and the evaporation time scale, you get something which is the Planck mass square divided by the mass square, which is of course very, 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 very small. So that means the black hole settles down, it radiates and it settles down extremely fast. So this process is therefore quasi-static. Sort of the way, the rate at which its geometry is changing and the mass is reducing is much slower than the rate at which the geometry is just settling down. So what you can model this process as is as a one parameter family of black holes of decreasing mass. So at one instant you look at it, it looks like this with some mass. At another instant you look at it, the same Penrose diagram with the lower mass. That is how you model it. And for each one you can do Hawking's calculation. Right? For each one you will get this thing with the mass which is going down. So these calculations will work very well until this is this quasi-static approximation, as long as this is much less than 1. So basically, until the black hole is some order of magnitude of the Planck mass, right? It will go on. This picture is something which we believe we can trust. So till the black hole is down to its Planck mass, it has been radiating thermally, all right, at a ever increasing temperature. And then in the last stages, we don't know. Quantum gravity kicks in, we don't know what happens. Yeah. Sure.
He settled down basically the time where the collapsing ends, something like that.
No. It's like I suddenly poke you, right? Then you take a few seconds. Settle down. That's exactly what it is, right? So your brain gets a stimulus. Your brain says, "Oh, it's not that important. It's only a poke or whatever." Because the eyes tell it that. Then everything equilibrates. It's not. You don't have a fight response. Just something normal. So similarly here, the black hole radiates, so there is some change in the geometry, and it equilibrates. How will it equilibrate? Roughly the time scale is how does this communicate, to all parts of the black hole, and then it equilibrates to another black hole.
This settle down time is related to something called scrambling time.
I don't know what scrambling time is.
There is something.
No, I mean I don't know technically what scrambling time is. So let's keep that separate. Okay? I don't know what scrambling time is. That's a longer debate. So then we put in quantum mechanics. I don't know. That will be a much more subtle discussion, which we can have after the talk. But right now, this is what I mean. Okay. You can, after the talk, you can just tell me what scrambling time is, and we can see whether there is any relation. But right. Okay. So what has happened is that at the end of this evaporation, right, you started out with this, right? Okay. And then at the end of it, you have something of Planck mass. Be 500 Planck mass or 10,000 Planck mass, but whatever. And you have a whole bunch of thermal radiation. Right? Now, when you created this black hole, you could imagine putting it either, this matter in a pure quantum state. Then it kind of gravitationally collapses, and then you have this black hole. But what you get out is a whole bunch of Hawking radiation and a Planck mass. Right? So this state is dominated by this Hawking radiation and is a mixed state, what you expect. So somehow you have gone from pure state to mixed state, and this is what is called intermediate. So you put all this information, this picture together, and this is the Penrose diagram which Hawking came up with. Right? So you start out over here, matter collapses, there is Hawking radiation. So the strength of the singularity kind of reduces over here. All the mass has been lost here. So over here, you have something which is of the order of Planck mass, right? And all the Hawking radiation has come out here. And here you have something which is more or less flat, because there is no mass in this space-time. Okay. So I just want to point out that maybe in 15 minutes, I will just give you the start of my talk, and I will just tell you the result. Okay, but that's all right, doesn't matter. So Hawking's technical analysis, right? What it did is that, as I told you, used the late time behavior of quantum matter on a fixed mass classical black hole spacetime. This is the fixed spacetime. Now, of course, that once you have the radiation, it has energy, and it will gravitate, and it will affect the geometry, right? And we have not technically written down all that. What we have done is we have said that because of these time scales, we will model the process as a one parameter family of fixed mass black hole spacetime. So that is your physical input. Technically, you have not taken into account what is called the back reaction of Hawking radiation. If you could do that and solve the equations properly, then you would get the same picture, because the picture is, has got a good physical underpinning. But it is true that we still don't have over here a calculation in which the back reaction is taken into account. I just wanted to point that out. Now, this is the Hawking view. Okay? But there is an alternate view to this, which is the relativist view. And this was first sort of articulated by the ANBR, Ashtekar, and Gojewald. And what they note is that the endpoint is not just something of Planck mass and radiation, but you actually have this singular boundary as well. And if you think about it, all the matter is really gone in over here, right? So if any information has gone, it has gone into that singular boundary. But what can happen, and what does happen in preliminary calculations of quantum gravity, but it could be any quantum theory. What seems perhaps plausible is that singularity, I mean, usually when you hit a singularity and things blow up, the lesson is that you are pushing your theory beyond its domain of validity. In this case, it is classical GR. So, on the other hand, you know that if the curvatures are high enough, before they blow up to infinity, they will become of the Planck scale. At that point, you would expect quantum gravity effects to kick in. And hopefully, if you have a nice quantum gravity theory, maybe you don't see singularity. So let us assume that. But once you have whatever your theories of quantum gravity, there are no real singularities in nature. It's an artifact of pushing classical GR beyond its terminal validity. So then this singular region is not, it's not really a singular, it's not a barrier where everything ends. Right? It's just some very quantum gravitational part of space-time. Okay. So what happens is that one expects this singularity to be replaced by some quantum region. Now when near the singularity, you expect very large fluctuations of the geometry. But you know that the concept of an event horizon requires the full geometry of the space-time. If the geometry is fluctuating a lot and you're not sure what it is, then really the concept of an event horizon is not very useful. Even teleological, but it's also not very useful because you don't know the exact geometry. And in fact, Hajicek has shown that if you take the normal collapse situation and you just fiddle with the geometry in a Planck scale neighborhood of the singularity, the event horizon disappears. Really is a global construct. So instead of that, but we already have something nice, right? Because I told you about these trapped surfaces and the light converging and all. So that's a good proxy for a black hole. And one defines, this is what I defined, a concept of a dynamical horizon, which is a smooth three-dimensional hypersurface related by marginally trapped two surfaces. This is exactly what the Vaidya situation was, right? So every point is a two-sphere. This is R, so it's a three-dimensional, marginally trapped surface, right? Foliated by marginally trapped two spheres. Okay, so and again, the Einstein equations themselves tell you that if matter falls in, these two spheres increase in area. If there is no matter at all, like for the event, when it asymptotes to the event horizon, there is no area increase. And when there's matter coming out, there is area decrease. So what really is evaporating in this picture, so, I'm sorry, I made a mistake over it. It is not that matter is coming out. It is that negative energy matter is falling in. That mistake here. Positive energy matter falls in, it increases in area. Negative energy matter falls in, it decreases in area and becomes time-like. So what happens over is that you have a dynamical horizon. It starts out space-like, goes on increasing as matter is falling in, and then becomes time-like over here. There is a quantum region. But what happens is that this quantum region is not a barrier to a quantum evolution. So a huge space-time region can open up beyond the singularity, and while the Hawking radiation itself is thermal and in a mixed state, it can correlate with stuff which is coming out of the singularity so that the net state is pure and purity is restored. So that is a proposed possible mechanism of alleviating the Hawking loss problem. But for that you need to assume that the quantum gravity resolves the singularity. Now this is just a qualitative idea. And of course, it would be good to check whether this qualitative picture is actually realized in some simple computable model where you can go a little bit ahead with the computation. Now, finding a full quantization even of a gravitational system or a model which displays Hawking radiation is quite difficult. Because technically you need a black hole, you need Hawking radiation, etc. And to have a complete quantization is already quite difficult. But a good first step would be as follows. Right? So as I said, Hawking's analysis was of quantum fields on a fixed geometry. It did not consider the effect of quantum Hawking radiation on the geometry. In order to do so, what one could do is try to replace the classical TAB, the stress energy of the collapsing matter, by its quantum expectation value. So if you could compute the expectation value of your quantum matter field on this geometry, some arbitrary geometry, and stick it in to the right hand side of the Einstein equations, then you would have something where the quantum part would also back react and contribute. So that is the idea. So we expect the back reaction of the quantum radiation on the geometry to be accounted for through what are called the semi-classical Einstein equations. But note over here that even for a scalar field, we have, as is normal, usual, products of fields at a point. And usually what happens is that if you have flat space-time, you have a simple prescription which is normal order. But now you don't have flat space, you have some general curved space-time, which is going to be a solution of this equation. So you need to do some point separation to regulate this object. And geometrically, what you do is that you separate them by geodesics of the geometry. You have something which is moving on a geometry, you take point splitting by those geodesics and you do something, you regularize, and finally you get some answer. Now this is extremely hard to do in 4 dimensions. We don't know how to do it. And the infinities are too virulent, we don't know what to throw away, etc. etc. But in 2 dimensions, one really knows how to do it. 2-dimensional geometry, especially with the conformal, one knows a lot about how to do this. Okay. Now let me go back and say that, well, what is the simplest context for gravitational collapse? Well, one may think it could be spherical collapse. Spherical symmetry, because in spherical symmetry, there is no gravitational radiation itself. So there are no degrees of freedom associated really with the gravitational field. It just reacts to whatever matter is put on. But even for a minimally coupled massless scalar field collapse, the classical physics is itself very complex. You have these things called the Chopwick effect, self-similarity, all sorts of crazy stuff. And one does not know how to compute the back reaction. Now, in the early 90s, Callan, Giddens, Harvey, and Strominger, they discovered a two-dimensional classically solvable Thorne model, which describes the collapse of a scalar field. And that scalar field, the coupling is that it is what is called conformally coupled to the 2-dimensional geometry. That simplifies life a lot. And this 2-dimensional black hole formed by collapse evaporates through the emission of Hawking radiation. And the back reaction is computable by some old methods of Davis and Fulling, precisely because it's 2-dimensional. And one can learn a lot from this model, but it has a couple of unsatisfactory features. I'll tell you what these features are, then I'll tell you what the model is which I am looking at, and then I can formally conclude. Want me to continue? I can continue as you wish. So this is what. So now we are in 2 dimensions. It's not 4 dimensions with spherical symmetry where everything was a 2-sphere, right? And you had past and null. This is genuinely 2 dimensions. So you have the full plane, right? And you have a left infinity where something goes to minus infinity and right infinity where something goes to plus infinity. So therefore, you have 2 spatial infinities, right and left. You have 2 null infinities which are in the past, left and right, and 2 future infinities, left and right. Now, this particular solution of Callan, Giddens, Harvey, and Strominger is very special. It involves a situation where you only have right moving, this left moving matter. It starts on the right at prime minus, it's a 0 mass field, and it goes to the left. Now, and it forms this structure. But here is the crazy thing. If you go and you look down from right stripe plus, of course you don't see the full space time. So from the right there is a black hole, perhaps. From the left also you don't see the full space time. Maybe there's a black hole from the left. However, when you go in detail and you find that stripe plus right is geodesically complete. That was the first thing I mentioned. Whereas stripe plus left is not geodesically complete. So this singularity is left naked and right closed. Right? So all the interesting stuff about the Hawking radiation is from something. If you put a scalar field in its vacuum over here, then there is radiation over here. That is the Hawking radiation. But the stuff which is curving the space-time and collapsing it and carries all the information is going from the right to the left. So obviously, it's very difficult to now talk about a good way of getting out back the information. Then all the information is going to the sick place and all the thermal radiation is going to the healthy place. So that is, you can still learn a lot, but you are hampered by this. And secondly, because the geometry is completely different, and it is really, if you look at it, it is the delicate nature of the blue shifting which happens between stripe plus right and stripe minus. That really depends on the detailed nature of the geometry. And the geometry here is not GR, it is whatever is the model. And you find therefore that the Hawking temperature over here is independent of the mass. So you don't have this profile where the temperature goes on increasing. It's just flat. So therefore, it doesn't capture what we want to capture very well, and the aim in not in this talk, maybe in some future talk, is to do better. So let me just tell you what are the features of the model, right? And I will then jump to the last slide and tell you what one does. Okay, maybe that is the best thing. So I consider a system with the following features. First, the geometry is very simple. So wherever there is geometry, it obeys the equations of G. Einstein tensor is equal to some stress energy. I haven't told you what is stress energy. Now, I'd like to restrict attention to space-time with only one set of infinities, and that means that the symmetry axis at r equal to 0, like in Vaidya, I have to tell my equations or my formulation that the axis is in the space-time. Otherwise, I get a Kruskal-like situation with two infinities. So the axis has to be, and that can be done by putting boundary conditions on the fields. What about the matter? The matter is spherically symmetric scalar field. But if I just let it be a minimally coupled one, then I would have this Choptic effect and so on. So I alter the coupling because I want a solvable model. There is nothing wrong with the matter. It still is positive energy matter. There's nothing wrong. But I make it the coupling depend on the areal radius. And when one does this, what happens is that when you integrate away the angular dependence, because nothing depends on the angle, remember there was a two-dimensional metric sitting there, which didn't have the angular part. You find that the matter is conformally coupled to this two-dimensional metric, and then you can use all the techniques of two dimensions to find the stress energy density. And so you can write down the semi-classical Einstein equations. Okay, so one can compute the quantum back reaction. Not only that, the classical solution turns out to be just a Weidler solution. So, so that is what happens. You can really write down the semi-class. So you have good control on the classical solution. It's the Vaidya solution. So you can go and compute a Hawking effect of this same conformally coupled scalar field as a test field, and you will find Hawking radiation at the Hawking temperature. So you have a Hawking paradox, exactly as I mentioned at the beginning. But you can also put in quantum back reaction, write down the semi-classical Einstein equations. Now these are not then analytically solvable, but miraculously, unknown to people that this was this same model, people had done some numerical work on it. So I can combine the most of numerical work with some analytical understanding and get a semi-classical picture. Then it turns out that while it turns out that the singularity is still there, even in the semi-classical field. Right? So let me just go over here. So this is what the semi-classical picture looks like. Right? It's a mixture of some analytic stuff, some numerical stuff which was there earlier, and some physical intuition. So what the semi-classical picture looks like, which would be really confirmed by a modern day simulation. I encourage somebody to do it. So this is exactly like Vaidya. You have a flat part. Now the Vaidya singularity would have started here. It moves down a little bit. So that is what happens. Again, you expect a dynamical horizon to form, and when the matter collapse is dominated by the classical matter, it increases and then turns around, and when Hawking radiation starts, it becomes like this. And here it is just one set of equations. It's not that you're modeling things, etc. This is just the semi-classical Einstein equations. And then it turns out that the simulations show that this dynamical horizon, which is this marginally trapped, one parameter family of surfaces, goes and meets the singularity in the interior of the space. And therefore, you have a last ray, which is what is called a Cauchy horizon, because beyond this, you don't know what the evolution is. Beyond this and this, because you have the singularity and you don't know what happens. Right? Now, even though the semi-classical equations you expect will break down over here near the singularity, where fluctuations are large, and you don't have modeling by expectation value, but fluctuations become very important. Nevertheless, out over here, where you expect the geometry to be asymptotically flat and not singular, you expect the semi-classical equations to go. So what one can do is one can go over here, make some physical assumptions about the geometry here, and do what is called an asymptotic analysis. When one does that asymptotic analysis, one finds that the semi-classical equations give you what is called a Bondi balance law. So what happens over here is that you start out with the full mass of the spacetime, which is the ADM mass. And as you go up, there is Hawking radiation, right? And so the mass starts decreasing, and there is a precise way of measuring that mass, which is decreasing, which is called the Bondi mass. And you can write down the semi-classical equations tell you the rate of change of Bondi mass and tie it to the total stress energy which is being received over there. That stress energy has a classical part and it has a quantum part, which I know because we can write down the semi-classical equations. And if you analyze those equations in detail, then this is what they look like. This is the rate of change of Bondi mass. This is a classical part, and this is a semi-classical part. The classical part has a definite sign because it obeys positive energy conditions. But the quantum correction is of indefinite sign. So we cannot say sometimes it, I don't know enough. So what is this U bar? U bar, so when we go out to infinity, right, there is an asymptotically flat coordinate which is U bar, and that is a function of this initial coordinate chart which I used. Is called x minus. So there is some function over here which is used. One can manipulate this equation and bring some of this stuff, even though you don't know what it is, to the left hand side, and you can get something which looks explicitly positive definitely. So here you can identify this with a quantum corrected Bondi mass and this as a flux, and so the quantum corrected Bondi mass decreases as U bar increases. And U bar is actually the asymptotically flat coordinate over here. So you have already fixed a conformal chart over here, x plus and x minus, but this x minus is not necessarily an asymptotically flat coordinate here. U bar is the asymptotically flat coordinate. You don't know what U bar is without actually solving all the equations, but you can certainly say that whatever is U bar, the Einstein semi-classical Einstein equations tell you that there is this balance. So now what you may say is that the black hole goes on radiating until it exhausts all its Bondi mass. Not its original classical Bondi mass, but the quantum corrected one. When it does that, then both the classical flux has to vanish and this quantum flux has to vanish. Both of them have to vanish. And when the quantum flux vanishes, there is a derivative over here. So it means that this double derivative vanishes, which means that U bar is a linear function of my x minus. And this x minus was what the matter is conformally coupled, so it just sees a flat space-time, doesn't see the conformal factor, and this fiducial flat space-time is coordinated by null coordinates x plus and x minus. So it is that x minus which is of the fiducial flat structure, not the actual curved structure. The actual curved structure is U bar. However, the upshot of all this is that the semi-classical Einstein equations tell you that when the corrected Bondi mass vanishes, the flux has to vanish, and if the flux vanishes, both this olive term vanishes and the red term vanishes, which means that this U bar is now a linear function of x minus, which means that when x minus goes to plus infinity, so does U bar, and when U bar goes to plus infinity, so does U bar. So it tells you that the physical prime minus is as long as this fiducial prime. In the Vaidya space-time, as well as in the semi-classical space-time, this terminates at a finite x minus. The code breaks down because now you have a Cauchy horizon. But the asymptotic analysis hints at an extension of this prime minus beyond this point. So when you put everything together, then this is the picture which emerges. So let me just summarize and conclude. So I've told you a whole lot of stuff, right? The upshot of it is that I wanted a computable model where I could see whether this restrictive Poisson paradigm, there was some evidence for it. What I could do was provide a model where you could classically solve it and get the Vaidya solution, which is a very well-known black hole solution. You could do Hawking's analysis on that solution, and you could get Hawking radiation at the right temperature, unlike in this VHS case. also this had only one set of infinities. And while you do not trust the semi-classical equations near the singularity, you do trust them near stripeless, where you expect the metric to be almost flat. And when you do an analysis over there, stripeless, it generates supporting evidence that the physical stripeless is as big as this fiducial stripeless where this scalar field was propagating. So if you put everything back together, and you look at the scalar field, it turns out that if you switch off the scalar field, you get flat space-time. So all the 2 degrees of freedom of the theory reside in the scalar. The scalar field itself propagates on this bigger space-time, and it is conformally coupled. So it does not. It only sees this flat space-time without the conformal factor. The singularities are all contained in the bad behavior of the conformal factor. So it looks like the scalar field can just go through the single. So now this is qualitative. This is what emerges through various different strands of evidence. So it seems like you have a scalar field, it just goes through over here. This region probably is now going to be replaced by a quantum region. This, from the semi-classical theory, we know is going to be a dynamical horizon which becomes time-like over here. The matter field, it turns out, the classical matter, because this is the axis of symmetry, right? The classical matter just goes, it just goes through. Axis of symmetry is just a point. So when light rays come, they just go through this point. But if you look at this sort of a diagram, where you just cut off this part, because it's a sphere over here, something is going through here, over here it just looks as though it is reflecting. So what happens is that, this is just classical theory, right? So this scalar field, which doesn't see the conformal factor, just goes through the axis and reflects off over here. It comes out over here, this is that olive term of the classical scalar field. And then you have perhaps some more quantum radiation, which was the red term. Finally, the Bondi mass, the corrected Bondi mass is exhausted, and over here you have flat space-time and you have an infinitely long span. So and then one can make further arguments and also have supporting evidence of the fact that the state over here is pure. So it looks like this gives you some supporting evidence for this. So basically that is what I wanted to say, but I really wanted to communicate the Hawking puzzle and all those things, because that is what will stay. Tomorrow this may be proved wrong, something else may happen, but the puzzle and what the GR part was, that is there. That is there for you guys to solve. So, thanks.
Questions?
Yeah, nice
Yeah.
talk, Madhu. So, way you handle this paradox, correct me if I'm wrong, but in this case, under the Woodward, argument was that there are correlations between the. But in your case, is it actually correlation which is saving the Hawking paradox?
Yeah.
So, can you just elaborate on what?
So what happens? So you see, of course, what. So let me go slowly. The point is that because this is a subtle viewpoint, something which has to be said, right? The scalar field itself, right? So if you look at the scalar field, then it is conformally coupled. So remember the metric. This one should go. Okay, so the metric was, it looks like this. I'm just telling you what it is because I didn't have time to go through the whole thing. So here you have. So this is the standard, and then you have the angular measure. This is sin square theta, whatever. This is just the flat space time. If you go to x plus minus is equal to t plus minus x, then this is just minus b squared plus bx. Now, because it's conformally coupled, actually It just this it satisfies the curved space Taylor question, but that also reduces to the flat space Taylor. So the scalar field then just is a sum of left and right movers subject to some boundary condition that they reflect off this axis, which is it turns out the axis is at x equal to 0. So with x equal to 0, you have the scalar field. And just, so this is without switching on gravity or anything. Right? This is what the equation for the scalar field is. But now, when you want to compute the semi-classical Einstein equations, you have to compute the stress energy. That stress energy depends on the background metric, right? So it's not, we can't just normal order it. The stress energy is sensitive to curve. But nevertheless, the scalar field is not sensitive. Now, if you speculate that the 2 degrees of freedom, certainly in classical and semi-classical theory, they reside in the scalar field. So if I speculate and say maybe there is a quantum gravity theory, that quantum gravity theory also lives on this arena. It's all speculation. I don't know if it's true. Then, because the 2 degrees of freedom are in the scalar field, the Hilbert space of the scalar field is the Hilbert space for the entire system. All the other operators will be written in terms of the scalar field operators if you could ever construct such a quantum gravity. So now what happens is the following, that you put the scalar field over here in a coherent state. And you take the expectation value, then you will get the classical part, which is what I wrote down, and you'll get vacuum fluctuations, which are what you do for semi-classical gravity, and you can write down semi-classical. So all that is fine. But you are given the initial state, which is a coherent state. You are given that the actual space-time manifold is exactly as large as this fiducial Minkowski. It is not half of this or anything like that. So now you know that this evolution is simply unitary, right? So the scalar field, which was in a pure state here, will definitely come to a pure state over here.
There is no, I mean, in that sense, there is no loss.
So so what the only thing which you have to do is to reinterpret this scalar field in terms of the freely falling observers over here. Now the freely falling observers, if you only look, in the classical theory, actually the space-time is cut out over here. So if you look at the freely falling observers here, right, and you look at how they interpret this state here, because you don't have access to all of Scribe-Class, this will be a mixed state. And you can ask what the freely falling guys see over here, and they will see exactly Hawking equation at lead times. Now you come to the semi-classical theory, where you have a slightly larger Scribe-Class, but all indications are that the real Scribe-Class, that this just ends at finite time. That is what the indications are. I'm not sure it. Somebody should do a proper numerical study. If that is true, and if my other supporting arguments are valid, then actually the quantum extension is the whole of Scribe-Class. And therefore, if you only ask about what these guys are seeing, then they will say, well, till here I have a mixed state, right? Because this only in the last stages something crazy happens. But Hawking's arguments hold. So almost up to here, I have this thermal radiation of different ever increasing temperature. Something happens over here, right? So this state is mixed. But if I have access to the whole of Scribe-Class, then you will see that correlations are slowly being restored. Now, there is some very interesting work which sort of I am also will be involved with soon, which is related to this. So just stop me if everyone wants to go for lunch, or I am just just tell me when to stop, because I can go on forever. This is no problem. So you can ask different questions. So let's change tax a little bit. So very often there is this heuristic picture, okay, that which is absolutely, I don't like it. I think it's wrong and it's counterproductive. That that just outside the horizon, some vacuum fluctuation happens, and a pair of virtual particles are created.
Around
Around, and it's very misleading. So one guy becomes real and comes out, and the other guy becomes so. But that kind of gives you some picture that the kind of quantum which is here has a partner. If that partner could come out somewhere, it would purify this quantum. So there are a bunch of people in LSU, Ivan Aguyo and Jack is very good postdoc and a student. So they wanted to really ask the question in a technically nice way as to what exactly does it mean to be a purifier. And it turns out that there is a, I mean, you can talk in private. There's a really nice way of looking at. So, this goes back. I don't know how much is familiar to people here, but again, this is something which VR people and do in curved space-time. In quantum field theory, in curved space-time, and in general, there is for any linear field theory, scalar field theory on space-time. You can construct a Fock space for that scalar field. And that Fock space is it derives from what is called a one particle Hilbert space. That one particle Hilbert space itself derives from what is called a complex structure. Then you can define from the complex structure and the symplectic structure something which is a Hilbert space, which is a one particle Hilbert space, and the symmetrized product of this then becomes a Fock space. So using all those structures, they are able to say if there is a mode, what is its purifying mode? So there is a very precise concept of that. And basically what it means is that if you take a certain mode, a certain element of the one particle Hilbert space and look at all the particles in that particular mode, which in colloquial language would be, I look at Fock wave packet with peaked at some frequency, and I look at all particles which are approximately of that frequency, that is like a mode. Then there is a precise definition of a partner, and what that is the following. In order to measure a mode, you have to do some local quantum field measurements all along. It cannot be purely local because of this business of positive frequency and relocalization of particles. But roughly speaking, you can do set of local measurements on one part of sky plus amplitude. You can ask the question, is there a very precise sense of measuring some other mode which corresponds to local measurements on the other part of sky plus, such that if you only make this measurement and that's this measurement, right, the state which you get, right, which is you can trace over all other degrees of freedom except these modes. Is that state pure or not? Actually, there is an answer. There is precisely one mode which you can assign to this mode which makes this state pure. So that is called the purifying mode. And what they have shown is that if you have a Hawking mode which comes out, the purifying mode comes out, actually doesn't come out in the conventional picture because there's a singularity which intervenes. But if you assume that singularity is resolved, it comes out way into the future, much later. So it is not just this picture of one mode which is there on the horizon and all that. There is a mode, there is a purifying mode which comes out much later, and that correlates with this. So one can do a similar calculation here. That is what we are trying to do. See where exactly. So you can really answer your question with quite a lot of precision, and it is correlations which are coming out.
That'd be nice once these results.
Yeah.
Any other question? So I have a quick question. So you have been talking about 2D gravity basically. Does this can you generalize this to 4D?
So there are two things. One is like real 2D gravity, which is what CG doing. I'm not doing that. Okay. I'm doing genuine 4-dimensional gravity, but
Slice.
But I am choosing a coupling which is I'm just doing this because it will answer your question very quickly. Okay. So
This one.
it's simply answered by. So the geometry part is just the Einstein-Hilbert action. Okay, exactly. 4-dimensional gravity. Integrate over the angles, you get something. Right. So this is the 2-dimensional curvature. This is the areal radius. These are only degrees of freedom. So you get something. don't worry about the kappa, you can set it to 1. What about the matter coupling? So the matter coupling, you see, if it was without the purple term here, then it would just be a minimally coupled scalar field. But I'm introducing this 1 over r square. You see, it's still a 4-dimensional thing, but I'm just introducing this 1 over r square by hand. Okay? So the 4-dimensional matter coupling then reduces after integrating over the angles in spherical symmetry to this. But the model is 4-dimensional, the geometry is 4-dimensional, which is why I get the Hawking temperature to be 1 over m, etc.
So more precisely, my question is: are there gravitons in the semi-classical curve?
So here there are no gravitons because I'm in spherical symmetry. So if you go any spherical
Fluctuation, right?
and
You'll have non-spherical fluctuation.
right. So here the model is because you want to compute with it. It's completely spherical. You switch off
You switch off gravity.
all no, not gravity. You switch off
No, gravitons.
you switch off gravitons. So any non-spherically symmetric modes are switched off. It's a midi superspace pattern. So it's a midi superspace which is spherical gravity with a matter coupling which is not the convention. So and that is part of the reason was because otherwise you will not get technically anywhere in this. And of course it might be that the more complicated you get, maybe these simplistic pictures are modified to the extent that they are no longer valid. But that's
I mean, one question. So when you are telling that you are switching off the gravitons, so if you go very near the singularity, can you actually deal with gravitons here?
so what happens is that you see, uh, so one is coming at it in a different view. There is a paradox, which is the Hawking paradox, and this paradox is there. It doesn't involve any approximations. Gravitons will also be radiating, and they will also have their temperature, and everything is there, and this is a problem. Now, you want to find what are the ideas that you can circumvent. One idea is that actually, which is what Subrat pursues quite a lot of papers, is that actually somehow, in some strange way, the information actually comes out in some correlations between Hawking quantum which are emitted later and which are emitted earlier. But if you do that, then you have to do other things which are more exotic. Complementarity, not measure both inside the horizon and outside the horizon. So that is one way. Another way is that people just give up and say that the information just vanishes. And so that's the way it is. That's what Hawking. The third way is to say effectively the same thing, but that information has gone in some baby universe which you have more access to. A fourth way, which is, to my mind, in all these exotic things, least exotic, is something which seems to me at least, because I work in this area, to be more logical. Namely that the singularity is not actually a singularity. Singularity is a place where your physical theories break down. You can look for better theories. So if you don't give up hope and you say that there is a better theory, then that better theory is quantum gravity and it should resolve these singularities, then a huge area, something opens up beyond the singularity and you have a new playground. Using that playground, you can speculate on a possible mechanism for information recovery. Okay. Now, this is just a qualitative picture. So slowly you want to do what you always do. You want to slowly endow this picture with some quantitative precision. For that, you need a simple model. In that simple model, what you want, the robust feature over here, which is there, is singularity resolution, Hawking radiation, or classical backward. So these are the essential features you want to keep, and this is already complicated. And you don't want other features which will make your life more complicated. In this simple case, and that is why one switches off gravitons over here because it's too difficult to deal with. But certainly, in a realistic situation, all hell is breaking loose in the singularity. You can't say that no, the life is only going to be spherically symmetric. That's completely ridiculous, right? I mean, there will be, as Amitabh said, There will be fluctuations everywhere. There will be all sorts of madness will happen there. But can at least the fact that if you resolve the singularity, can information be recovered? It's a small, robust question one is trying to answer, as in most cases you do things with models. This is also what people do for the Big Bang, right? When you do Big Bang, you do homogeneous. You just shut out all the other modes. And at best, you treat them as perturbations after last step. But at the quantum gravity level, you can't do it. So there again, you do what is called mini superspace computation. You patch together. You say that maybe the physics is actually dominated by some particular modes. Maybe that is the problem. And in fact, that has some support, at least in the cosmological situation. You can read it up. It's called the BKL conjecture. Okay, so there is a kind of universal behavior as the you approach the singularity, where it looks like decoupled homogeneous isotope, homogeneous anisotropic. So due to Berinsky, Lifshitz, and Karatnikov, and there is a lot of numerical evidence. So you might actually, so some of these things may say, okay, you don't have gravitons, you have independent cosmologies that are defined. I mean, there's lots of stuff. So you can ask elementary ones, or I'm here for the postcard. Even if they're what you think of basic, there's nothing basic. They're all quite deep issues.
Okay, and this